Welcome everyone from my side to the Meet the Experts talk today. As introduced, I will talk about our tool, the AreaMatch tool in the KODAQS Toolbox today. As announced, my name is Anne Strappe. I'm a postdoc here at GESES. I'm working in the survey data curation department, and I'm also working for the project KODAQS, and I'm there in charge of tool development as well as a coordinator in our academy and teaching there on data quality. And my area of expertise when it comes to data is mainly the linked data track. So everything when it comes into linking survey data and mainly with geospatial data is kind of my area I'm working on. By training, I'm a political scientist, so my research topics are focusing on how spatial disparities influence political attitudes and also voting behavior. But on the other hand, I'm also doing a lot of research on spatial linking techniques and methods, and you can reach me under my email address here at GESES. Since I am a political scientist, I would like to start this talk today a little bit with a more like substantive research question, a motivation from political science. And when we think about voting behavior and political discontent in political science, one kind of re-emerging topic in the last decade is the question if rural areas serve as breeding grounds for political discontent and far-right voting. This is not only something we observe in Germany, but also across Europe and in the US. And there's also not a new topic in political science to ask how the spatial context, how the neighborhood is influencing individuals and their political attitudes and political behavior. And from a theoretical point of view, this is very intuitive, I would say. So we on the one hand, we would say, okay, in rural areas, there might be less public services. They are weaker provided with public service and infrastructures. We also often see an economic decline or a demographic shrinkage in these areas, as well as a stronger attachment to local identity. So very strong kind of identification with the rural ideas, with values, with more traditional values, and also more cultural threat perception. So those are kind of characteristics that are often assigned to rural places and therefore argued this is the reason why people living in those rural areas might feel that the state is not caring for them as much as in urban places. They are not recognized as much. And they're also just not getting the fair share from the government. And therefore, they often tend to either have lower trust in political institutions, but also being attracted by the idea of far-right parties that say we have to change the status quo and kind of sell themselves as advocates of those people living in these rural places. If we contrast this with the empirical results of this kind of research question here in Germany, then we do see that rurality alone is actually only a weak and often also not a sufficient predictor of AfD support and right-wing sentiments. And we also see that this kind of explanation doesn't work in all regions of Germany in the same way. So often we see there might be a correlation between living in a rural municipality and supporting the AfD, but this might only be the case, for example, in East Germany and not that much in West Germany, where we have the support for the AfD often stronger in some urban areas compared to rural places. And there's also the idea that the rural-urban divide might not necessarily overlap with the deprivation divide. What do I mean with that? So local economic decline and also service infrastructure might be weak, but there might not always be also in rural areas. So especially when you look in the south of Germany, we have a lot of rural areas they're doing economically very fine and are not as weak as we might expect. So not always is rurality this equals a weak economy or a weak provision with public services. And this kind of theory empirics clash that we find here might not only be something we could think about from a theoretical perspective and explain from a theoretical perspective, but that also might be one driver of these kind of findings that we have like a strong methodological challenge when we ask these questions, want to analyze those questions. So when we want to test those spatial theories like living in a rural place affects those outcomes, then we usually require, on the one hand, individual information on the individuals. So we want to link individual attitudes and behaviors with those local conditions. And this implies a need for, on the one hand, geocoded survey data, and on the other hand, contextual indicators that are somehow consistent, that are comparable, and also spatially aligned with those survey data and survey information. So the core data quality question I want to focus on here is, how do we link individuals to places in practice, and how does this choice actually affect in the end our substantive results on this research question? When I talk about geocoded survey data, I mean survey data that have a direct or indirect spatial reference. That means they contain some information about the place an individual that is asked in a survey and interviewed in a survey is living. We often have also geocoded survey data that are already enhanced with spatial data attributes. For example, the ZERP has this data set where you already contain some characteristics of the place a person is living, either the municipality or the district or the federal state. But the huge kind of challenge is that those data are usually restricted due to data protection regulations because of course, the information of the living place is one of the most sensitive characteristics of an individual we can kind of publish and give out when we publish those kind of data. At GESIS, we have geocode survey data for 4 of our main survey programs, for the German longitudinal election study, the FREDA panel, as well as for the ALBOS and the GESIS panel. And what you usually find is that you can access an additional data set with regional identifiers in a safe room at GESIS, where you then can do your analysis, and basically you get your results of your analysis and can take you with them and write your paper or your research project based on those. But all the analysis, all the linking is done in-house, so you don't get your regional identifiers for your own analysis at home, for example. Since we talk about political attitudes and voting behavior, I will just shortly talk a little bit about the GLASS, because that's kind of the basis of our example for this talk and also for the tool I want to present. And when we talk about geocode survey data and information on respondents' locations, this always depends a lot on the survey data we have, how they are sampled, but also kind of which information we can release or we have asked or collected in the survey data. So for the GLASS, we have here those different surveys that are rolled out during, for example, last year's election. And when we just want to focus on kind of the local information or the regional unit information in those surveys, then we have, for example, the cross-section survey of the GLASS, which is based on a register sample. So there we have like a 2-stage sample process where first we sample the municipalities, and then we get a random address sample from the municipalities and invite the interviewees via post. And for other samples, like the panel or the tracking, there we actually collect those information on the respondent's location within the survey. So we actually include question on the zip code, so the postal code where respondent is living. Because we don't get this information from the access panel where we actually run those surveys, but we actually have to collect this during the survey process. And the zip codes are often collected because this is actually an information everyone knows. So I might know the village I live in, of course, but the problem there is that often those information, when we collect them as like an open answer field, there are a lot of error, they're very error prone, and people might not be like familiar with also the correct administrative unit that I'm living in. If, for example, my small village belongs to a bigger municipality, then this is again like a next step for people, for the data curation afterwards, to actually match this correctly. So zip codes, we do argue, is usually the one that people know by heart, what the kind of their zip code is and their address. So this usually helps when people need to kind of put in the information on their own location and residence. But still, there are a lot of source of uncertainty when it comes to these information. So especially when we talk about those zip codes or the self-reports themselves, of course, we have uncertainties and errors that are coming from those measurements. We also have the problem of residential mobility and temporal change. And we also have errors when it comes to the spatial unit alignment. Talking about the measurement via self-reports, so zip codes and CAVI surveys, we observe in our own samples that we have about like 10% of non-response or unvalid responses to this question. This means that people just type in some numbers and they're just not correct and do not match with a real valid zip code, or they just do not answer this question. And of course, even if we have like a valid zip code, we have no control mechanism of people actually entering their own correct zip code, or if they just like make one up, maybe take the one from their work address or whatsoever, because they are not willing to actually share the real zip code. And this is a very old study, but there is a study that actually shows that we might have reporting difference between gender, education level, and age. This means that this might not be just a random process of people not sharing the information, but there might be some systematic bias driving this as well. When it comes to residential mobility and temporal change, we have the issues on the one hand that the respondents themselves might move between the sampling and the survey actually be carrying out, but also between, for example, in a panel study, different survey waves. So we actually don't know if a person, when we ask them some questions about their political attitudes or behavior, is still living at the same place that we expect the person to live, because we collected the information at a different point in time. And of course, and there's a challenge, especially in the kind of smaller administrative units, that we have a lot of redistricting happening over time as well. So, for example, small municipalities are often put together for administrative reasons, and then we actually have a change over time of municipalities. And that's like the last challenge of the second temporal change. The context information we want to link to our survey data, they also should match the year we collect our survey data. So if I'm interested, if, for example, some characteristic like the population density, I'm most likely interested how dense is this area populated in the year the survey was collected and not 10 years ago or 5 years ago. You might be interested from a theoretical perspective in, like, for example, the change, then you also need this kind of information. So this matching the survey year or the survey collection and the context information is also one of the crucial steps. And there can also be some uncertainties if just the context information are not available for specific years, or a range of years as well. And lastly, and this is kind of our main focus here, it comes to the spatial unit alignment. So especially in Germany, and it's kind of a hard case for this, we often have the issue that the survey and the context data, the regional information we collect there, they not contain the same spatial units. And this is why I'm talking a lot about today about zip codes and municipalities, because especially there, we often have this mismatch and an ambiguous kind of match and overlap between those two spatial units. For example, especially in rural places, there might be one large zip code area that may contain several municipalities, while we often have in an urban area that within one municipality, we might have hundreds of zip codes. For example, in Berlin, this is the case. Because zip codes are designed to have the most efficient kind of districting to deliver mail, while municipalities just have this administrative reasons why they are districted like this. Another example for Germany is, for example, that we also have constituencies that are then again overlapping with all of those units in a different way, because they are designed to contain always 250,000 inhabitants. So again, there's just another logic of how those spatial units are designed and why they are like sized and shaped in a specific way. And this kind of then clashes and creates the problem that our merging isn't that easily, and also creates measurement errors in the end. And because of that, because of exactly this problem of overlapping but incongruent boundaries, and because we kind of experienced this in our own research a couple of times, that we had survey data with zip codes, but then context information only available on a municipality level, on a district level, or constituency level, we designed this tool AreaMatch in the KODAQS Toolbox to kind of help and give some guidelines on how we can improve this matching and assess the quality of the matching process. So the challenge here, this linking of spatial units that overlap but differ in shape and size, and then the goal to provide replicable code to guide through this linking process. And we introduced there 3 different matching methods. So on the one hand, centroid matching, areal matching, and areal interpolation. In the next minutes, I will just go through this tool and introduce you to the different matching methods and how we compared those different methods. When I say we, I also want to mention my 2 co-authors of this tool, that's Stefan Jünger and Fabian Stressegger, who are also working in the same department as me, and who are working on this tool that was published in 24 already online, so you can access this via the KODAQS Toolbox. When we start with this tool, or before we start to actually dive into the tool, I want to talk about data prerequisites and the setup of the tool. So on the one hand, and this is what I was talking about already, we have kind of our target data set, and this is survey data with a region identifier, so geocoded survey data. In this case, in this example, we have the GLASS tracking of November 2023, and our variable of interest here is AFD rating, so saying how much do you like or support the AFD on a scale from 1 to 10. And then as our source data that we want to link to our survey data, we want to link population and area of municipalities to measure the population density. And what we also need, besides kind of the geocode survey data and the context data, we need also spatial data, so shapefiles for our target and our source units. So in this case, we need the definition of the German zip code areas as well as the municipalities. All of the tool and the code is based on basically 3 R packages, and it's all run in R. And this is the simple features package. This, I think, overall, the package we always kind of recommend when working with spatial data in R. It's the most up-to-date. It's also working in a tidyverse framework. So if you work in R already in tidyverse, that's super helpful because it just follows the same logic and it's at all the main and most useful commands and that you need for spatial data handling. And also we use the ggplot2 tool, of course, for visualizations in this tool. And what really helps when you work with this tool, I think, is some kind of basic knowledge of how to handle spatial data, or what, for example, is a shapefile, what is vector data. I also won't talk too much about this in this talk, but just basic understanding of this, I think, would help. But we try to design this tool in a way that basically everyone can follow through this tool without such a deep knowledge of kind of what is behind that. And you see on the right-hand side here a little bit of the setup section, and throughout the tool you always have this kind of code sections and code snippets that can be copied and pasted. So you can basically run this code while you learn about the tool, and we also provide all the sample data. Of course, we do not publish the survey data, the real survey data with the real region identifiers, because we can't. But we provide some synthetic data, so you can actually run all of the tool with the data that is shared there as well. So diving into the tool itself, the first step is actually inspecting first the target data. As I said, self-reported zip codes can have some issues, and they might contain non-responses, typos, invalid entries. So it might also affect your spatial linking quality. So the first step we usually do is to check those zip codes. So first, check against the valid zip list. So actually detect the non-responses and the non-valid answers. And then, if possible, also cross-validate the information. So you might have, for example, another self-reported variable like in which federal state do you live? Is the zip code actually located within the federal state? So does the interview partner actually give a consistent answer? But also, for example, you might have some paradata on the residence by, for example, the interviewer or so. So you can actually flag inconsistencies you might find there. And then there's the big question of what to do actually with those cases. If they're not too many, I would always say there's the way to filter them and just keep the valid and consistent zips for linking. So this is totally fine if you say, I don't think I have like a big issue with that. If you're able to, you might want to correct or impute zip codes because you might have some paradata information that allow you to do that. If there are really a lot of invalid and inconsistent answers on this, and they might be systematic, then this, of course, is a bigger issue. And then this might be the problem, or the way to think about is actually the linking possible and feasible or not, and should be done or carried out at all. And of course, one last very important step is also how that we report how we proceed already in this step to just know how many cases and observations we're already losing when we validate the zip codes. In the example we provide for, we have 6.3% of our respondents who didn't give a response to the question to enter their zip codes, and also 1.7% that gave us an invalid zip code. We're proceeding with this like 8% of missing data as it is, so we just like filtered them and worked with the rest of the data. But of course, this is something like a first step that you always should consider. The first method, the centroid linkage, I want to begin with. So here, I think it's the most straightforward method. How do you want to link, or you can link your data sets? So you can use the geometric center of each zip code and identify the corresponding municipality. So in which municipality is this centroid located in? What we assume here is that the centroid adequately represents the zip code's location within the boundaries. And you already see in those kind of two graphs that this can work quite fine, and intuitively you would say, okay, maybe in the first one, this makes a lot of sense, while in the second one, it doesn't. So it really depends a lot here on the shape and the size of those different units. The strength of this approach is that it's very simple and it's computationally very efficient. So especially if you have like large data sets, that's super helpful. And it's just a very quick and straightforward linkage. But as I said, on the one hand, the centroid may misrepresent where people actually live, or also where land use is concentrated. For example, we have a lot of zip codes in the cities, in, for example, districts or areas where a lot of offices and businesses are located, and there might be only residential living areas in a specific part of the zip code. So here, the centroid might not represent the place where actually people live, and this might be an issue for your linkage process. And also with the centroid linkage, we ignore the shape and the actual area that overlaps between the zip codes and the municipality, and the area that overlaps could be very, very small. So we might misclassify units or link units that we wouldn't like intuitively link with each other because of those irregular shapes and fragmented areas. So one solution to kind of overcome this problem is the areal matching solution. Here we basically calculate for each zip code the overlapping share with each municipality, and usually we link then the two units that share the largest overlapping area, so the largest share of its area. So here we do have the strengths, and we do consider that the full geographic shape actually of the areas, and we have like an actual spatial relationship between the zip codes and municipalities that is considered and reflected in this linking process. The limitations here, when I already say we calculate each overlapping share of each zip code with each municipality, this can become computational intensive, especially if you have a lot of units. In Germany, it's already like kind of if you really match all municipalities in Germany with all, that's like around 10,000, I think, with all zip codes, this already can take some time. If you have even larger countries or several countries, as I said, this might then become a little bit more computational intensive and just take some time. And we also have the issue that we here always need the decision when multiple units overlap, which one we match to each other. So here we typically tend to just choose the ones that have the largest overlap, but there might be some ambiguous cases. We plotted those ambiguous cases in our case for this tool. So we actually had a look at the map of ambiguous zip codes. So there, the zip codes where we actually have like multiple overlaps. And when we look at them a little bit more closely, we see that we have around half of our sample zip codes that overlap with more than one municipality. So here we really have like the issue of not knowing which municipality to link. But if you look at the overlap shares, then you see that 90% of that, often 90% of the area overlaps with one municipality. So 90% of a zip code is overlapping with only one municipality. And then you might say, okay, in this case, I'm pretty confident that my linkage, when I just link with a municipality with the largest share, is right. But kind of the other case then is when we have zip codes when there's very few cases only where we have near equal overlaps. So it's like when it's like a 50-50% case, then it might be complicated. And I think the like pinkish red ones on the slide are exactly those zip codes where you have like a nearly equal overlap, and then it might be more of a coin flip, which when it comes to the largest share. Still, if it's only so few cases, then linking based on the largest overlap is usually unproblematic. But as I said, when you might have more of those kind of very ambiguous, nearly equal overlaps, then you might want to think about making all linking options available and run sensitivity analysis based on, is it like the largest share, the second largest share, and so on. And I also always would advise to plot those kind of cases where you have ambiguous linkage situation, because then you can see if they cluster in any location, in any specific region, and if they're like any, like if you can see like strong correlations with, for example, the population size. In this case, we do not have this like strong concentration. This, for example, in Germany, what you often see is in this like administrative units that we have some concentrations sometimes in some federal states. This doesn't seem to be the case here. We do have like a slight correlation with population size, but it's still like in a kind of range where I would say this that we can still use like the largest overlap here very well. The last method we want to look at is areal interpolation. And this is kind of the most complex one we introduced in this tool. And with this method, you link, or it distributes the municipality attributes proportional to a zip code based on the area of overlap. What does this mean? So for each zip municipality overlap, we actually compute the intersection area, and then we weight the municipality attribute, so here population, by the share of the overlap. So the smaller the share, the less weight has the average population of a municipality for this calculated population characteristic, because we sum in the end across all overlaps for a zip code. So we basically get a sum of all the population sizes of each overlapping municipality, but we weight it by those, the share of the overlap. So this allowed us to actually account for multiple overlapping simultaneously, and it's very flexible when it comes to irregular boundaries and also the varying unit sizes. So we actually can like acknowledge each overlapping area and each size and each shape, and we get all the information and include all the information we have available in our calculation of the population in the zip code. Of course, here, again, we have the issue or the argument that we assume a uniform distribution of the attributes within municipal areas. So again, as I said before, when it comes to the zip codes, also in a municipality, we do take the average population of a municipality, even if the zip code only has like a 10% overlap with this new municipality, and we don't know if even any people live basically in this area that is overlapping with our zip code. So this assumption may not hold in reality. And of course, this is even more computationally demanding. And what it requires, and that is not always the case that we have it, is that the matching attributes are actually available during the linkage process. So especially when you work with geocoded survey data that already have the region identifier provided, or they even already have the attributes, you might not be able to perform this linking process if you don't have all information and you do not do the linking by yourself. In the end, we, of course, want to assess the quality of our linkage methods. And to do that, we kind of have the challenge in our example that we do not know the exact location of our respondents. So we do not have any addresses. We do not have like a ground truth to what we can compare our data. So what we suggest in our tool is that we run a simulation approach. So we sample basically 1 million hypothetical living locations for each respondent in for our sample. So we collect 1,000 random points within each valid zip code area and simulate the information And what we do with that is that we want to create a ground truth data set. So we say, okay, for every simulated point, we know the exact municipality it falls in because we have the point location and we can do a point matching in this case. And this allows us to obtain a simulated true number of inhabitants for that specific location and then average over this information of this 1,000 random points to kind of get a measurement for our quality of the linking methods. And what we look at the first step in this quality assessment is the accuracy of our measurement. So we compare the three matching methods against this ground truth estimate, which we simulated based on the point location. So we just take the difference between our simulated real inhabitants per municipality against our estimated inhabitants per municipality. And what we find is that for the majority of our cases, differences are actually close to zero and rather small. So we see that it's rather accurate and that all three of our methods show also a very similar accuracy. So we don't see like huge difference between those three matching methods. There's one note on this. This might not only be the case because our matching is so good, but if a zip area overlaps with a cluster of municipalities that all have a similar population size, then difference will be naturally smaller. And we do have the case, right, that we have often municipality, for example, a rural municipality with a low population density that's more likely to be adjacent to other rural municipalities with a similar population density. And of course, then our accuracy estimate would be small by nature. So this might be regardless of the method here. Another comparison we look at is how consistent our three matching methods are. So do those matching methods come to the same results, basically? So we take here the difference between the results of each matching methods. And what we find here is that all of our three density curves are actually centered around zero. So difference, again, are not that huge. And the methods produce quite similar estimates, especially when we compare areal matching and the areal interpolation matching. So here we see this on the very left, the graph, we see they have very narrow density, so they're very small and also consistent in the differences. When the other two graphs are comparing the centroid matching with area interpolation or areal matching, and here we actually see that on the one hand, the graph is slightly wider, so we have a more variability of differences, and also the higher peak that indicates that a larger magnitude of differences here. So we see for both that there's like some differences in the consistency for sure. Lastly, we also kind of identify what of our matching methods kind of gives us the best estimate. So we see which methods minimizes population differences across zip codes and map this best performing method here. So in the dark purple, we have the zip codes where the areal matching is performing the best, and green is the areal interpolation performing the best, and in yellow, the centroid matching is actually performing best. And what we see is that, again, most areas perform similar, but differences are clustering in some spatial contexts. For example, in densely populated areas, the zips often lie within one single municipality, and then the centroid matching just performs very well and very easy because it's not such huge problems with like the overlapping areas. And what we also see in this graph is that area interpolation usually performs best due to the incorporation of all the spatial information. So the differences to kind of the real estimate is just like so much on average, just smaller than compared to the other two methods that then area interpolation usually performs best on average across all zip codes. In the end, we're, however, interested actually in our substantive impact. So coming back to kind of the first question, the correlation of population density with AfD rating. So are people living in rural places actually more supportive of the AfD in Germany? We just compare here the correlations between AfD ratings and population density matched via the different methods. And we use here not the absolute population size, but the population density to focus on this like spatial context. And again, what you see here on the right side is that the correlation coefficients across those methods differ only very marginally. So they kind of perform similarly. And from a substantive kind of viewpoint, we do see that higher population density is negatively correlated with AfD ratings. So people living in more urban places rate the AfD lower than people living in rural places. But this relationship is here very small and close to zero. Of course, this is just like a very basic correlation. So this minimal difference in a bivariate setting might change when we look at, for example, multivariate or multi-level models here. So saying this, when feasible, there's still kind of the point to make that conducting sensitivity analysis across matching methods in a multivariate and multi-level setting should be done just to ensure the robust substantive conclusions that don't depend on the different matching methods. In summary, as I said, the centroid matching is very efficient. It performs very well when linking zip code areas amongst municipalities, especially in cities. But this has, of course, some drawbacks. The areal matching needs some investigation, especially when it comes to ambiguity in the overlapping places and some decisions on this. And the area weighted interpolation is the more accurate in the end, but computationally also the most intensive. So there should also always like the question is if it's really superior, do we actually need to put in that more effort if it's really providing those consistent results in any case. For us, I think the best practice kind of message is always to do those kinds of robustness checks to at least like select 1 second method to link, just to ensure that findings are not driven by the use matching processes. Coming to an end here, I also want to kind of guide you to like further resources when it comes to these kinds of questions. So there are even more advanced methods to assess and minimize those kind of linking uncertainties. So I want on the one hand mention the areal package by Chris Freena and colleagues, who basically looking at the area weighted interpolation, but give you like a few more advanced methods and also build on the SF package a little bit more advanced kind of settings in to adjust the area weighted interpolation. So this is definitely something to look at. And also our colleague Jonas Lied, he's working, so that's currently under development, but he's working on a geo-imputation package where we basically tackle the problem of do we actually know or where's the person actually living. So exactly the issue of if I have like a zip code area and I know where kind of their residential area is, it's more likely that a person actually lives in this residential area and not like in this business area. So how can we actually make a better prediction where our respondents are living? And finally, when it comes to geospatial data types and linking methods and analysis, we also have a couple of workshops here at KODAQS training. So we are teaching in April our course on Introduction to Geospatial Techniques for Social Scientists and are together with my colleagues Stefan and Dennis. So there's kind of a shout out if you're interested in that to join this course, where we also talk a little bit more on raster data and other linking methods like point-to-point linkage and stuff like this. And also the advanced geospatial data processing course by Stefan and Dennis, where they talk more about also different data sources like satellite data and how to integrate those and link those with survey data. And finally, Tobias Rittenauer is teaching geodata and spatial regression analysis in July as well. And yeah, I hope you got like a little bit of an insight into our tool. The KODAQS Toolbox is providing more of such tools, not all focusing on geospatial data and linking, but all of them kind of focus on one issue or one data quality issue and how to evaluate those data quality issues for social sciences. And we try to provide a resource here that on the one hand gives you code and replicable information on how to calculate those key quality indicators. We also provide always interpretations and recommendations for all those steps and offer some accompanying learning possibilities like quizzes to work with and actually test your knowledge and what you've learned afterwards. And we hope that we can like give everyone with different disciplinary backgrounds here some information and some help to tackle those kind of issues. But we're always open to comments, to questions. So please reach out, check out those different tools as well if you're interested in it, and just give us a heads up if you have any questions on those. And also, if you're interested in KODAQS, on the right-hand side, you have our QR code. We're also starting the third cohort of our KODAQS Data Quality Academy. So you can actually sign up for this now. And we also have more upcoming Meet the Experts talks. We're also tackling some KODAQS tools.